Well, language is fascinating, and Hal is one of the major experts in this area. So.
Okay, so that's very loud. Can you hear me okay? Yeah. All right, so thanks for having me. So I actually changed what I was going to talk about at the last minute to make it more representation learning-y. So the first half of this talk is going to be mostly about unsupervised learning, and then the second half of the talk is going to be mostly about supervised learning. And I'm super grateful to Chris, who did an amazing job of like setting up the stage for what I'm going to talk about. Okay, so I do language, right? So what is natural language processing, right? So we want to build systems that can understand language in some way that people do. There's tons of work in sort of this middle layer where you're trying to do things like speech recognition, translation, information extraction, question answering, and so on. And so I sort of stole this entirely from Chris, right? So like Chris was saying, in 2017, the way you do NLP is you build a BILSTM and you throw your training data into a BILSTM. This works for lots of tasks, right? So you might have some sentence like Arthur shall strike the blow that sets Lucy free. You train your BILSTM to do named entity recognition, and it says Arthur and Lucy are both people. You might train your BILSTM to do syntactic parsing, and then it'll generate some sort of dependency structure over the sentence. You might train your BILSTM to do machine translation, and then it'll produce something in German. I don't speak German, hopefully that's correct. You might train it to do factoid question answering, and so then when you get another input like who wrote this, it will produce, does anyone know? No guesses? Okay, so it's Bram Stoker, so this is from Dracula. Dracula's gonna be like the running example. But then there are other problems like what I'll call complex question answering. And so I might ask, what does Lucy need to be freed from? And so this is a much harder question to answer, right? So we need like much more knowledge about the context in which this sentence is being uttered in order to accurately answer this question. And since I told you it's from Dracula, maybe you have some guess about what she's being freed from, but we'll get there later too. Okay, so what am I not going to talk about? So I originally was going to talk about learning language through interaction. There was almost no representation stuff in that talk, so I figured I'd drop it and talk about something that has more representation. Besides, if you want to see that talk, it's linked from my webpage, so you can watch it offline. Or if you're really bored during this talk, you can watch it now. I'm also not going to talk about like bag of n-grams plus logistic regression. So Cho at NYU calls me bag of n-grams guy because every time there's like some BILSTM result, I'm like, oh, I have to try bag of n-grams with logistic regression, and often this like works like almost as well as like whatever fancy stuff you throw at it. Usually you lose a little bit, but to be perfectly honest, if you asked me what representation do I use as my off-the-shelf representation, it's bag of n-grams plus logistic regression. Yeah, so I'm also not going to talk about things like averaging, which Chris mentioned, but if you're interested, we can talk about this offline. Okay, so I'm going to talk about this sort of long project that we've had for a while on trying to understand sort of the nature of narratives. And by narratives, I mean both fictitious narratives like you'd find in books and real narratives like you'd find in newspapers or history texts or something like that. And the thing that I want to sort of highlight here is that we're going to try to do this in a totally unsupervised way. And so there's been a bunch of talk earlier in the morning about sort of like what is like an objective for unsupervised learning. And our objective for unsupervised learning is very clearly, I want to produce something that people can understand in a meaningful way. And so, I guess this is largely my view of unsupervised learning in general, is that you're really trying to take a huge amount of data and whittle it down to something that like a human can understand. Now, obviously, that's really hard to quantify, but that's sort of the direction we're going. So I'm going to talk specifically about relationships. So I think this is important for understanding like social behavior and how humans work. And sort of my normal story is if you want to build like a digital assistant and the digital assistant doesn't understand how humans communicate with each other and how humans interact with each other, it's going to be super unnatural. So we want to understand social behavior. So speaking of relationships, these are my two students who did pretty much all of the work that I'll talk about in the first half. So Snigdha is a postdoc at UIUC now, and Mohit's just graduating. Okay, so there's been a reasonable amount of work on trying to understand narratives from the perspective of roles that characters play. So like this character is the hero, or this character is the villain, or this character is whatever other type of characters there are. But a lot of narratives are really about the relationship between multiple characters. So if you look at something like Calvin and Hobbes, for instance, it's not really clear like who's the hero or the anti-hero, who's the antagonist, and so on. It's really just a story about how their relationship evolves over time. And this is true for a lot of relationships. And like the two things that we're going to go after are the fact that relationships aren't static, that they change, and that we don't know a priori like what types of relationships exist in the world. So that's going to be the unsupervised learning part of the problem. So this raises the question, how do we describe relationships between two characters? So this is from Tom Sawyer. So this is a plot summary of Tom Sawyer. So Tom falls in love with Becky and persuades her to get engaged to him. Their romance collapses for various reasons. And then like by the end of the book, like they end up becoming friends again. And so when we first started looking at this problem, we looked at this from like a pretty straightforward like binary classification problem, right? Like basically, are you friends or are you enemies? And like how does this change over the course of the book? And so you can set this up either as a supervised learning problem or an unsupervised learning problem with sort of HMMs or something like that. But the thing that was like even more interesting than just looking at the progression of relationships over time is the fact that you have these effects that like, the friend of my friend is probably my friend, and the friend of my enemy is probably my enemy, and blah, blah, blah. So you can set up sort of like a little graph model that looks at triangles and character relationships. And so this is an example when we applied this model to Wikipedia's article on the 2003 invasion of Iraq. So basically, it decided that Hussein was not friends with basically everyone else, and everyone else was friends together. So is this an accurate representation of like what happened in the 2003 invasion of Iraq? No, like obviously the relationships which were much more complicated than just like we work together or we don't work together. So this sort of raises the question of like, given the fact that there are lots of ways that characters can relate, how can we represent this in like a useful computational way? Okay, so I'm going to go back to the story of Dracula, and I'm going to look at Arthur and Lucy in particular. So at the beginning of the book, I'm going to assume that maybe people haven't all read the book because you didn't get the question answering problem right at the beginning of the talk. So at the beginning of the book, Arthur and Lucy get married. So I'm going to think about this as sort of a distribution over a bunch of different types of states. So maybe there's like some love going on, there's some joy, and there's some marriage. And then later in the book, Lucy starts feeling bad because she got like bitten by a vampire or something. So she feels weak and worn, and so there's like the sort of predominant theme at this point is sickness. There's some sadness, but like Arthur and Lucy are still in love. Then Lucy dies, so you then have something that's mostly about death. The love has gone down, so the relationship between Arthur and Lucy sort of devolves over the course of the book because she gets more and more enamored with Dracula. But then like, okay, plot spoiler, she's not actually dead. So then at the end of the book, basically Arthur has to go kill her for real. And this is when he's striking the blow that sets her free. So then we would say that this is predominantly about murder. There's not so much love going on, although there still is a little bit. And then there's like this weird fantasy bit because because she didn't die when she died. Okay, so this is going to be the passage of time. I'm going to talk about the passage of time as a trajectory, and then I'm going to talk about these things as states. So why did we want to do this in the first place? So there's a lot of work in the humanities about trying to understand recurring themes in literature. So I've highlighted 3 examples here. I'll just read maybe the middle one. Or maybe I'll read the last one, right? So can we detect positive or negative subtext underlying meals between 2 characters? So this seems like kind of obscure. And I think this came largely out of a study of like Dostoevsky novels. So apparently like how characters interact when they're having meals is highly indicative of what's going to happen later in the book. And so you can obviously do a close read where you have a person like read as many Dostoevsky books as they can, but you can also imagine trying to automate things like this. And so one of the reasons why we're looking at multiple states at any given time is because often we want to look at things like subtext, where it's not just the primary thing that's going on like sickness, but also other things that are going on at the same time. Okay, so we have this data set of character interactions. This is extracted from Project Gutenberg. So we take a pair of characters. We extract spans of text that mention both of them. So this is from the book Confederacy of Dunces. So we have 2 characters, Ignatius and Mrs. Riley. So we find spans of text in which they both appear. And we do this throughout the course of the book. So I'm going to make a totally unrealistic assumption, which is that books proceed linearly in time, which is obviously not true. You could try to fix this, but we haven't done that yet. Okay, so the way that we're going to model this is through sort of like a dictionary learning over time type model. So the reason that we're doing dictionary learning, or this also looks a lot like topic modeling, is because we want to end up with results that we can actually show to people and that people can kind of understand. So we're going to assume that we have this dictionary, so each row is going to be a topic in sort of topic modeling terminology, or a state in like my state trajectories example. And then each span is going to be a probability distribution over states, right? So this span, for instance, might be like 70% about love, 20% about sadness, and 10% about suffering. And so then if we want to sort of show this to people to have them understand it, we can say like, okay, at this point in the book, the thing is predominantly about love. Okay, and so the basic model that we're going to build is some sort of recurrent autoencoder with dictionary learning going on in the middle. So I'm going to step through this in a bunch of steps, and there's going to be nonlinearities in places. So let me go through one piece at a time. Okay, so at each point in time, we're going to have some span of text that mentions 2 characters. So in this case, it's Mrs. Riley and Ignatius. We're going to take word representations for every word in the span of text. And we're going to do the thing that makes Chris very sad, and we're just going to average them, because that kind of works. We're also going to have a specific embedding for each of the characters. So we're going to have the Mrs. Riley embedding, and we're going to have the Ignatius embedding, which will, of course, be learned. And then we're going to have an embedding for the book that tells us what book we're looking at. Okay, so we take these 4 embeddings, we pass them through a simple affine transformation followed by a nonlinearity to get some hidden representation for this point in time in this book. We then do a standard recurrent thing. So we had a previous state from the previous time step, and we combine that with the current representation to get a hidden state at the current time step. Let's see. So what do I want to say here? So I guess the important thing here is that our states are going to be probability distributions over the different topics. And so we're using a softmax activation to get something that looks like a probability distribution. Okay, so then we take our probability distribution over states. We multiply it by our dictionary matrix, which will also be learned. And this gives us the representation at this point in time. Okay, so now we finally use this representation to reconstruct the input, where in our setting, the input is this average representation of the text span. Okay, make sense?
So use the same model to reconstruct or some new export?
So this is, so we're minimizing squared error between these two between these two vectors. Yeah, Russ?
In the embedding of sort of these characters in the book, is it edited? So you have the embeddings and then you just add them up?
You mean this part?
Yeah.
No, so this is, we take them, we concatenate them, we multiply them by, we hit them with some big matrix, and then we like tan H it.
And so this, this summary, this current state, encapsulates the emotional state of each of the two people as well as the state of their relationship?
We hope so. Yeah, so there's going to be two things that are going on. I mean, I already sort of hinted at this in the example, but there are going to be some parts, this was further back than I remembered, right? So there are going to be some parts that are going to be about the relationship, right? So like marriage or love or something like that. And then there are going to be some parts that are really just about one character or the other, like the death example. Yeah?
So sometimes when people talk about dictionary, there's a sparsity in the coefficients. Do you have that?
Yeah, so we tried this. We couldn't really get it to work, so let me put this back up, right? So the place where you would naturally put sparsity is on this guy here. So trying to think exactly what we tried. So we tried various versions where like you softmax and threshold. We tried other things where you like ReLU, then renormalize. I think those were the two things we tried. And it never really seemed to help much. These did end up reasonably peaked. I'll show some examples later. But we didn't get a huge amount of leverage out of sparsity.
What's the dimension of the embedding?
So these, the word embeddings, I think 300.
And then the next one.
Yeah, and I think that, okay, so I believe these are 300. It stays 300 here. And then this becomes basically a preset thing, right? How many topics do you want in your model? I think it was either 50 or 100. I'd have to look to be sure. Okay, so how does this do? So here's like my, I can't remember what Russ called it. This is my thing to, it's like showing pretty pictures, right? What's that called? Anyway, these are my pretty pictures. Pretty pictures in language land are not as pretty as pretty pictures in yeah, the beauty contest. Yeah, right. It was Leon who said this. Yeah, so this is our beauty contest, right? So this is us. This is more standard topic modeling. So the main thing that sort of happens is that the sort of standard topic model likes to pick out like very concrete things and not very relationship-y or emotional things, whereas the RNN tends to like to pick out both. So I can show you, these sort of cherry-picked examples. The sort of standard way of evaluating these things is a word intrusion task. So we do this thing on Mechanical Turk where I show a Turker a list of these 5 words, and then I insert another word like taxis, and then I ask the Turker to pick out the word that doesn't belong. So if the Turker is able to pick out that word with high precision, then my topics are good. If the Turker is not able to do that, then the topics are bad. All right, so does the evaluation task make sense? All right, so here's the answer to your question, what K was. So here are 3 different settings, so 10, 30, and 50. I think the rest of the results I'll show are on 50. So we have a bunch of sort of baseline models. So what's being plotted here is for the different approaches, what's the precision on this word intrusion task, so higher is better. So for instance, here it's about 0.78, which means 78% of the time a Turker was able to pick out the intruder word accurately. Whereas here, for sort of simple topic model, it's about 50% of the time. Random guessing would be 1 out of 6, because we show them 5 words and 1 intruder. So the overall picture is that the 2 variants of our model, which I won't go into the details on, are markedly better than both sort of standard topic model-y things as well as topic model over time type things. So there seems to be something that's being captured here.
So it seems very important what word is interjected into this.
Yeah, so you have to be careful. So one of the things that you have to be very careful about is the word frequency. So you neither want to introduce very frequent or very rare words. So the standard thing that you do is you pick a random intruder that's about as frequent as all the other words in the topic, so that you're not just picking up frequency effects.
So where in the model, I missed this, was there anything about relationship, like as opposed to just topics?
Yeah, so I guess the main thing is that if the model wants to, okay, so in these spans of text where there are multiple characters, if the relationship between the character is important in the sense that it affects the words that are being written, then the model needs to capture that relationship in order to accurately regenerate this. So it's not like, we're not explicitly forcing it to do relationship. We're sort of encouraging it by the fact that we're giving it the 2 characters that it's supposed to be looking at, and it's supposed to use these to help do a better job of reconstruction. But it's not designed, there's no sort of like explicit cross-product term that's trying to focus on just the relationship.
Oh, you're looking at the neighborhood of those 2 people?
Yeah.
Those same people over.
Yeah, over the whole course.
That's where it's a relationship between them.
Yeah, that's right.
I'm not sure whether there are 50 relationship between these 2 persons. You know, like I guess because it's 50, you can even list all of them and see. So are there any overlapping between this?
Yeah, definitely. So I think actually I'll have something about this. Actually, was there another question over here? Yeah.
Yeah, do you have evidence for this working well because it's a recurrent net or because you're introducing relationship information?
Yeah, so I don't think I have it on this slide. So we did do an ablation where we just removed the recurrent connection, and things do get worse, but I couldn't quote for you off the top of my head how much worse they get. So essentially the difference here and here, there are 2 things being confounded. There's the dictionary versus topic models-y thing, and the recurrent. Actually, this has, right, so these are all non-neural, this is neural. These are non-temporal, this is temporal, these are temporal, but I don't have the neural non-temporal showing. But it is worse, it's somewhere in the middle. Okay, so, right, so here's the other way we tried to evaluate this. This is super difficult. So here's the trajectory. Okay, so the way that we're generating this is over time we pick the most likely topic at each point in time, and then lay them out linearly. And then we're going to give people plot summaries of the book and ask them which sequence better represents the plot summary that you saw. This is the actual thing that we produce for Dracula. So at the beginning of the book, it thinks it's about boats. So in case you haven't read Dracula, there are no boats anywhere in Dracula. It's not at all clear why it thinks that it starts with boats. For some reason, like, it really likes boats. It produces the boats topic everywhere.
Dracula, it's called the Demeter. It's how Dracula.
Oh, that's right. I forgot about that. Okay, so there is a boat in Dracula. Yeah. Okay, I feel so much better now. But that said, it does produce boats all the time for, like, I don't know what reason. So this is, I guess, actually a case where it's good. Okay, so this is the sort of thing that we produce. The sort of best of the other models, which is the non-neural but temporal model, tends to miss subtle changes. So it basically says the book is more or less all about love, and misses like all the key things that happen in the book. Okay, so we show these to people, and I'm worried that I deleted that slide. I did delete that slide. Okay, so I'm just going to tell you, people in general prefer our things to the baseline things by, I think it's like 70%. So we give them a forced choice, which do you prefer? And it's about 70-30. That said, reading these things is super difficult, and if you're not like an expert in the book and you don't know that there are boats in the beginning, you might not make a great decision. So I'm a little bit more dubious about this evaluation than about the intruder word task, which I think is much more clear. Yeah?
Are you getting the names for the topics?
Yeah, so that's a good question. So we name them. So, but without we don't name them like looking at the trajectory and naming them, right? So we have this list and then we come up with some term. There are techniques from like topic models land to do this automatically, but we didn't bother.
How do you compute model precision?
So model precision is the mechanical Turk task of intruder detection. All right, so so people here probably don't care about humanities, so I'll skip humanities. So this, the dictionary learning plus neural net thing actually seemed to work out pretty well because we were really looking for things that would give us somewhat interpretable models. It's definitely far from solved, right? Like this thing, not clear that it's really that interpretable. But it's sort of moving in the direction of trying to make things where like a person can actually look at the output and make sense of it. But I think that the sort of main point that I want to make is that you know, we care a lot about like showing the output to people and making sure that people can make sense of it, right? So the word intruder task is an example of that. And I think it would be nice to try to think of unsupervised representation learning from the perspective of like how will people use this output in a useful way for whatever task they're trying to answer, whether it's like a humanities task or whether it's something else. Okay, so the other thing that we care a lot about is common sense, right? So if I go back to my example of you're trying to build a little like robot to interact with people, it should both know about how people relate to each other and also about how people relate to the world. And this is often sort of referred to as common sense, right? So if I get something like Lex Luthor's limousine came late today, the driver had overslept, we're all very good at inferring that the driver is the driver of the limousine and that the reason that he came late is because he overslept, but this is not, you know, explicitly stated anywhere in the text. So we're going to try to get at common sense reasoning from this data set of comic books that we collected. So I actually never read comic books ever in my life, but actually comic books are very well studied in the humanities literature. There are actually books written about comic books. So here we have two frames. So in the first one, someone says this is where they buried her. The legend is that if disturbed, her ghost will rise. And the other person says, well, that's a good ghost story, Mavrakos, but I can't let it stop me, blow the roadblock. And then you get this thing where it says boom, right? And so we all know in reading this that the thing that's exploding is the roadblock. And we know that this is going to be bad and that probably a ghost is going to come out because that's sort of how it's been foreshadowed. But it's not stated explicitly anything about what the relationship between these two panels is. So in sort of the study of comics, this is called closure. So closure is the process by which we connect panels together. This also occurs in movies, right? So there will often be like jump cuts between two scenes, and it's your job as a viewer to infer the connection between them. Okay, so we have about 4,000 comic books from the Digital Comics Museum. This is from what's called the Golden Age of Comics, which is basically the 40s and 50s. We extracted 1.2 million panels with about 2.5 million text boxes in them. This itself was like an enormous amount of work. So we actually have neural networks doing all of the extraction of stuff and doing the OCR on the text. So this was not fun, but if you want the data, it's like 3 gigabytes, but you can download it. It's kind of a fun data set. So we're going to look at these sort of closed tasks. So this is a traditional language one, right? So the Simon's workshop has been interesting so far. I hope the rest of the week is just as something, right? And you're supposed to guess that the right answer is C, which of course it will be. So this is sort of this general problem of like, can you fill in what's coming at the end? So this is the task that we're going to have. So we have this scene, so this thing, whatever it is saying happy landing, sister, haha. Oh, poor Mr. Merriweather, he's gonna lose his job, and poor me, I'm gonna crash. Oh dear, well, crash, there's lots of crash. And then we get this panel, and this character is saying something. So the question is, what is she saying? So she could be saying, Alice, I've been looking all over for you. She might be saying, hiya, kid, all alone. Or she might be saying, golly, I'm still alive, but where am I? All right, so who thinks it's A? No one. Who thinks it's B? Who thinks it's C? Okay, everyone thinks it's C, right? It's obviously C. But in order to do this, like, you actually had to see what came before. Okay, so how are we going to do this? We're going to do it using BileSTMs, of course. We take the text panels, which we've run OCR on. The OCR is iffy, so you can't totally trust it. We run these through some LSTMs. We also run a standard convolutional neural network over the panel for the image part. And then we combine these through a standard like ReLU unit. And then we just do this over time across all of the panels. If there's no text box in the panel, then there's no corresponding connection there. And then finally, we have embeddings for each of the possible answers, which are extracted from adjacent pages in the same comic book. And then you're trying to predict the correct one. Yeah?
You said there's no text, but there is text. Is that not taken into?
So yeah, when I say text, I'm mostly referring to either thought bubbles or dialogue boxes. There's often things like crash and stuff like that, which it's sort of hard enough to extract this text. We just couldn't get this at all.
So it doesn't even go.
Yeah, it doesn't, I mean, the convolutional neural network might know that it says crash, but I doubt it, yeah.
More images with results.
Yeah, I'll answer that. All right, so actually that's a really good segue, right? So there are a bunch of like image and text data sets out there. So the most common one is this visual question answering data set, which came out, I don't know, maybe 4 or 5 years ago. And one of the sort of frustrating things there is that you can often ignore the image and do fine with just the text. So there will be like an image and there will be a question like, is there a steam engine in this image? And the answer is yes, because if there weren't a steam engine in the image, no one would have written the question, is there a steam engine in this image? So there's all these sort of like weird biases where you can effectively ignore the image and do fine just with the text. So that's not the case here. So we're always picking between 3 things. So random guessing gives you about 33%. If you use the images only and ignore the text, I mean, the text still appears in the image. So this convolutional neural network in principle could learn to do OCR as part of this task, but I kind of doubt it. So you get up to almost 50%. If you use just the text, you do slightly better than 50%. If you do image and text, but only in the current panel and ignore all of the history, you get up to about 60%. If you use the full context, and in this case, full context means previous 5 panels, you get up to about 63, 64%. Humans do markedly better. They get about 84%. We also have results for humans in the image only and text only conditions, but I don't have the numbers here. Humans also do much better when they have both.
How did you generate the confused text?
Yeah, so we had 2 settings. I'm showing I believe I'm showing the hard configuration now. So the hard configuration is we pick distractors from adjacent pages in the same comic book. So one of the things that happens in a lot of these is that characters have similar speaking styles. And so if you pick text from a different comic book, it's often just very obvious. So we also had an easy setting where you pick it from wherever. There you do markedly better, but this is the more interesting case.
I mean, that's why humans can only do 84.
Yeah, that's right. I think on the easy setting, humans were in the high 90s, I think. Not quite 100, but they were very good. Okay, so, so we have this new data set, which I encourage you to go play with. It's kind of a fun data set. I'll make the warning that it's from 1935 to 1955, which means that there's lots of not okay by today's standards material in that. It's kind of horrible, actually, but you can have the data set and play with it if you want. So we can learn this closure to some degree. We also did closure of images rather than text, so can you predict the next panel and stuff like that. The results were qualitatively similar. But we're like massively behind people, right? And this is not a case, I think, where it's a lack of data. We have an enormous amount of data. I think we just don't have enough to get at these like sort of common sense inferences. Okay, so let me just end with something that is kind of unrelated, but a lot of the talks earlier today made me think about this, and so I just wanted to spend like 2 minutes saying something here. You know, as sort of an NLP person, I feel like my job is to get inductive bias into machine learning systems. And this was fine when we were doing linear models. Like I can sit around and craft features, and that's very useful. But now in neural networks days, like I don't know how to like put a connection between this thing and this thing to get the right inductive bias. Like it's all very unclear to me. And so one thing that like my students He and Alvin, well Alvin's not technically my student, but He and Alvin did in this simultaneous machine interpretation task was some sort of data augmentation. So okay, so I'm not going to go through the background because I'm totally out of time. But basically, I want to do machine translation as you're speaking rather than waiting till the end. And so one of the things that you need to do, I'm going to skip the examples, is get things in an order that makes it easy to be monotone with the input. So in Japanese, I might say, we government structure and composition change should. Which the default translation would be, we should change the structure and composition of the government. But this is really bad from an interpretation perspective because you have to wait till the end of the sentence before you find out that you can say should change. So what we did was we reordered the output to be more like the order of the input. So we had a bunch of linguistic rules that said we can rewrite this sentence as the government structure and composition should be changed by us. And then this is much more in line with the order in Japanese, and we can be much more simultaneous. So we had a bunch of rules, right? So we parse the English side, we rewrite it in a bunch of ways, and we basically generate lots of new training data. And so we're then going to evaluate the translation system in 2 ways. So here what we're looking at is how simultaneous am I with the input? So how much delay is there between when like the Japanese speaker says a word in Japanese and I say the translation in English. So I want to be low. That means I'm very quick. And then the y-axis is how good my translation is, measured by blue. So I want to be here, right? I want high quality that's super fast. So this is evaluated against a rewritten test data, right? So we rewrite the training data according to these linguistic rules. We train a system. It's a neural MT system. It doesn't really matter. We then rewrite the test data in the same way, and maybe not surprisingly, the model that uses the rewritten data does better than the models that don't use the rewritten data, right? Because it's evaluated against data that's been rewritten. The thing that was surprising is that you get exactly the same effect when you evaluate against the original unrewritten data. So somehow what's going on here is I'm generating all this extra data that's like not quite perfect, but it's making my translation system better anyway. And so the way that I've been sort of thinking about this is we want to, like, I as a language person can cast my inductive bias as some sort of like transformations on the output that my system should be invariant to, and then I can generate fake data for this. Right, so like MNIST folks have been doing this for ages. They like rotate their images and scale them and blah, blah, blah. I haven't seen a huge amount of work on this in language land, but it seems to work well, right? So the way we've been thinking about this is sort of through covariate shift. So we're getting more data, which is good, but it's not quite right, which is bad. And so the question is like, where is the trade-off there between suboptimal but plentiful data? But I'd like to understand this better and maybe make this, this process a little bit more formal. All right, so with that, I'll end and take last questions. And there's stuff up there about what I said.
We have time for a question or two, and the next speaker can come up and set up.
Yeah.
Was there a concept of generalization for the relationships in the novels? For example, you bring up half of it and there is rest or the rest half of it, or
Yeah, so we didn't do that. So we basically, right, so there was no generalization being measured. It's just basically, does the model fit the data well? Yeah, Russ.
Out of curiosity, have you tried actually generating these, the sentences for, instead of just doing classification, you should try to generate the sentence?
Yeah, so.
Does it make sense? Because it'd be interesting.
Yeah. So the question was, have we tried generating the sentences rather than picking one out of three? So we didn't try this for basically two reasons. So one is evaluating sentence generation is hard, and we didn't want to get into that. The other is that the OCR errors are really non-trivial here, and so the text, so I'm showing you cleaned up text when I'm showing you the examples, but they're really, like the error rate on the OCR is like there's at least one error per word or something like that. And so we were worried that trying to generate that would just lead to sort of nonsense. But we didn't try it. I mean, it's obvious, right? We should also try generating the panels, right? Like I just want to write a comic book automatically, like write the first 4 panels and then it fills out the rest. I don't think we're there yet, but it would be fun.
Any other questions?
Oh yeah.
Let's pretend that there's a humanities person in the room. What are the implications that for the humanities?
Yeah. So I guess oh, you can go ahead and unplug. Yeah. So the most solid thing that we have is we have this paper, I guess under submission with Carrie Krauss, who's an English professor at UMD, basically looking at this question of so in sort of like Bronte Dickens type novels, like what's the relationship between, how does the relationship between characters map to essentially like socioeconomic status differences, right? So basically like rentier versus renter questions. And there's like some, like a lot of data mining things, there are some things where we rediscover stuff that people already knew, and then there are some things that are kind of new-ish. But it's definitely like just at the beginning.